In this lecture, we'll explore the first element of the DMAIC model, define. Remember, you can't make something better unless you define it. Fortunately, we have a number of tools and techniques that can help us with this task. I've found that using data and a team approach are two excellent ways to define an activity, process, or a problem. When you use data, you eliminate uncertainty and confusion. One of my pet peeves when it comes to defining something is the phrase more or less. If I ask a quality engineer about the dimensions of a part and she tells me it's 28 centimeters more or less, that's not good enough. But if she tells me it's 28 centimeters exactly, I feel much better. Also, when you define a problem with input from team members, the quality of the information and team member buy-in is much greater. We'll get started today by examining the basic Six Sigma metrics: defects per unit, DPU, defects per million opportunities, DPMO, yield, and rolled throughput yield, RTY. Next, we'll investigate a few team techniques to help define conditions and situations: brainstorming, brainwriting, nominal group technique, and affinity diagrams. We'll conclude the lesson by seeing how Pareto charts and critical to quality, CTQ, relate to process and problem definition. We have a lot to cover, so we better get going. Let's begin by exploring the concept of a defect. I'm sure that all of us know what a defect is. It's something that doesn't work the way we expect. If I push the power button on my computer and it doesn't come to life, it's a defect, unless I forgot to plug it in. A product is defective whether it has one defect or 20. My wife's computer may have more defects than mine, but nevertheless, they're both defective products. But there's no doubt that some defects are more critical than others. If the defect in my computer is due to a loose wire, that's not a big deal. But if my wife's computer needs a new CPU and hard drive, we better get out the credit card. Six Sigma uses defects to define levels of quality. Earlier, we said that 3.4 defects per million opportunities is the coveted Six Sigma quality level. Philip Crosby advanced the concept of zero defects in his book, Quality is Free. Crosby equated a defect-free environment with perfect products. Dr. Deming also commented on defects in his book, The New Economics. Deming ties in with our discussion of strategic planning earlier by stating that an absence of defects does not necessarily build business. Something more is needed: performance. In this respect, we all need to be careful not to make a product with low defects that no one wants. The thrust of Six Sigma is to identify and decrease process defects. Since just about everything is a process and defects are ever present because of variation, we have many chances to use Six Sigma. Defining current levels using defects per outputs is quite practical. It's easy to apply, works with practically any process, and useful for benchmarking with other companies and with your past results. The defining unit for our course is Sigma. To calculate Sigma, you need three pieces of information. First is the unit, what you make or service. Then there is the defect, output that doesn't meet external or internal customer requirements. Then opportunity, a chance to satisfy a customer or generate a defect. Many operations use defective products or services as a proportion, either as percentage defective or acceptable units yielded. For example, if a computer manufacturer tests 640 computers in a day and 25 have defects, The percentage defective is 3.9%. Calculating the yield is a snap. It's equal to 100% minus the percentage defective, which is 96.1%. Defects per units, abbreviated as DPU, expands on the defective products proportion by including all defects, irrespective of how many units have defects. Continuing with our example, the computer manufacturer digs deeper and finds that there are a total of 117 total defects found among the 25 defective computers. This translates to an average of 4.68 defects for each of the 25 defective computers, which is 117 divided by 25. And defects per units, DPU, of 5.47 for the 640 computers, which is found by dividing 640 by 117. DPU, while useful, is limited because it doesn't relate defects per unit to opportunities. For example, when it comes to testing computers, let's say there's 50 opportunities to satisfy a computer or generate a defect. Powering up the computer is one chance. Shutting down is another. So is operating quietly and reading information from a disk drive. The computer company can use another Six Sigma metric to help them determine and define quality, which is defects per million opportunities, DPMO. Some companies call DPMO parts per million, or ppm. The formula for DPMO is equal to the number of defects divided by the number of opportunities times the number of units times 1 million. So to calculate the DPMO for a day's computer production equals 117, which is the number of defects, divided by the number of opportunities, 14, times the number of units, 640, times a million, and we get 1,305.8 DPMO. We could refer to a partial Six Sigma conversion table that you see on your slide to see what level of sigma this represents. There's no DPMO that's equal to 1,305.8, but by using 1,300, we can estimate that there's around 4.45 sigma and 99.8% yield. Not too bad. When you bring the number of opportunities into the picture, it really makes a difference. Knowing how to calculate DPU and DPMO is fine, but most companies want to know the total yield throughout an entire process. Rolled throughput yield, RTY, is just the metric we need to define this. There are two ways to calculate RTY, one that includes rework and one that ignores it. While accounting departments typically ignore rework, progressive companies include it because it reveals hidden cost. Let's review an example from one of my previous jobs, making heart catheters. We made these catheters in 10 steps. Our RTY was 56.1%, not the best in the world, but here's the calculation that we used. And our RTY is not that unusual. It's common to have high operational yields above 90%, which you can see at the hyphenated line at the top of that chart, but also RTY at around 50%. So we now have a few ways to quantify process output. Let's shift gears and explore a few ways to capitalize on the collective brainpower of an organization.